These ligands or first messengers combined with this receptor in the membrane, it induces a biochemical cascade inside of the cell to regulate the biology and physiology. The first messenger doesn't have to go inside of the cell. All it has to do is occupy that receptor on the surface, and it's a three-dimensional conformational fit, like a key in a lock or a hand in a glove. Only those will fit together, and that's where the specificity of the interaction takes place. And while there are hundreds and hundreds of first messengers, there are a small number of intracellular second messengers. Cyclo-GMP was the first, then came calcium, then came cyclo-GMP, then the prostaglandins, now there's the peptides. So there are perhaps 6, 7, or 8. There'll be more discovered, I'm sure, in the future, and they too will probably get Nobel Prizes, I suspect. When cyclic GMP levels are elevated in the endothelial cell, it's elevated because of the production of a new molecule that I discovered. Even though it was an old molecule, we now discovered the biology in 1977, nitric oxide. Nitric oxide is one of these messengers. Nitric oxide is a very unique messenger because it's a gas. It's a free radical with an unshared electron in its outer shell. Therefore, it's very reactive with other molecules. It wants to fill its electron shell with an electron from another molecule, and it often oxidizes it. So it's very reactive. As you saw in the video, it comes out of smokestacks and automobile exhaust and cigarette smoke. It's a pollutant. Nitric oxide is unique because it doesn't have a charge at physiologic pH, unlike the other intracellular messengers. Therefore, it can go wherever it wants to go. It can go into the nucleus, into the mitochondria. It can come out of the cell and regulate the biology of adjacent cells. And in this cartoon, it goes over to the smooth muscle to make more cyclic GMP in the smooth muscle. And we discovered that that increases the relaxation of the blood vessel. And all smooth muscles behave the same way, pretty much. So this is the concept. Now let me tell you some of the details, and I'll skip through some slides so I won't overwhelm you. Nitric oxide, I believe, is a very, very old molecule. In fact, I wrote a paper, 7 or 8 years ago, but I stuck it in my filing cabinet and decided not to publish it. And then a couple of years ago, I said, I better publish this. I believe that nitric oxide was one of the very first messenger molecules in evolution. When organisms got started in the crypts of the ocean, near the magma boiling out of the earth, there were transition metals, gases, lots of toxic materials that came out of the earth. And the organisms living in this environment are very clever. And to protect themselves, they made ways biochemically to detoxify these substances. Well, bacteria are very clever because once they've created a biochemical pathway, why not begin to use that pathway to transmit information to one another? You know, once you invent the telephone, why not come along with a cell phone, or why not come along with the internet, or Skype and all these other advances? So the bacteria now started using these molecules to signal to each other, to feed upon each other, phagocytize each other, colonize and form multicellular organisms. So I think it was instrumental in evolution back 3.5 billion years ago. I can't prove that. I wish I could. If I could prove that, I'd probably go back to Stockholm again. But I can't prove that. I don't know how to design the experiment. But in the 1950s, 60s, it was recognized that nitric oxide and the family of nitrogen oxides are very toxic materials. They're all created from the combustion of fossil fuels. Wood, anything you burn with nitrogen in it will make nitric oxide. It's toxic. These nitrogen oxides are released into the atmosphere. They interact with ozone. They deplete the ozone layer, and ozone is important to filter out the ultraviolet light from the sun to prevent global warming. So when you have holes in the ozone, like over the Antarctic and other places, you enhance global warming. So the environmentalists became very concerned about the nitrogen oxides. and thought they were bad substances and pollutants, toxic. Well, I'm going to tell you that they're very important molecules in your body, and they regulate an awful lot of biology, and the list keeps growing and growing and growing. Furthermore, they influence a lot of processes and diseases, and there's a partial list on the right-hand portion of this slide to show you some of the processes, not only relaxation of smooth muscle, but they kill bacteria, they kill tumor cells, they play a role in inflammation, arthritis, a long, long list, and this will be more apparent a little bit later. When I began my interest with cyclic GMP, a couple of laboratories were also working with it, and they discovered some enzymes that produced it. These enzymes are called guanylyl cyclases. They have a lot of homology and similarity with the adenyl cyclases that make cyclic GMP. In fact, I think all of these cyclases probably originated from the same primitive gene that with evolution diverged to make the different cyclases. If you mutate one of the amino acids in the cyclase, you can make it become an adenylate cyclase versus a guanylate cyclase, so they're very, very similar. The cyclic GMP that is produced from GTP can be inactivated by a family of enzymes called phosphodiesterases. They hydrolyze the phosphodiester bond and inactivate the molecule, much as cyclic AMP is inactivated. There are probably 7 or 8 guanylate cyclases, isoforms, and we now find splice variants of these. We're doing a lot of gene regulation these days. And there are 11 isoforms of phosphodiesterase that hydrolyze cyclic nucleotides. Some selectively hydrolyze cyclic AMP, some selectively hydrolyze cyclic GMP, some do both. Now, the enzyme that you're all aware of, I know, is the type 5 phosphodiesterase that is found predominantly in blood vessels, and that's how Viagra works. Viagra inhibits that enzyme to permit the nitric oxide being liberated by the nerves in the corpus callosum of the penis to relax the blood vessels. When the blood vessels relax, they fill with blood. That's the mechanism of penile erection. And Viagra, therefore, enhances the effects of nitric oxide. We discovered that a long time ago, back in the 70s. Pfizer took all the credit, made all the money. I haven't gotten a nickel from any of that discovery, but that's the way scientists are. You give it all away usually. After going to Stanford, I realized that intellectual property can be valuable, so I started patenting things, but not until I went to Stanford. Most of these molecules, these messengers, regulate the activity of a protein kinase. There are probably a few hundred protein kinases. What they do is they transfer the terminal gamma phosphate from ATP to a protein substrate. And when the protein is phosphorylated, its activity can change. It can be activated or inhibited. So this is basically the mechanism of signal transmission and conduction in lots of systems. So it's rather simple and straightforward. Not so difficult, but that's not the case, because you have lots of isoforms of all of these enzymes, and you're not quite sure which one is doing the business and regulating what. So you can spend a lifetime trying to sort out all the details. Well, it becomes some interesting biochemistry. But I always believe that if you understand the details of the biochemistry, the physiology, you put this together and advance it into clinical medicine for a benefit. I'm not going to show you all the biochemistry detail. But in the process of looking at guanylate cyclase in some detail, we accidentally found that several small molecules activated the enzyme. Sodium azide, sodium nitrite, and hydroxylamine. We put these substances on cell cultures and tissues, including smooth muscle, and found that they elevated cyclic GMP levels, and we were using them as hormone replacements for the first messenger, to change biology and figure out what they were doing. When we put them on smooth muscle cells, and I thought cyclic GMP would cause contraction of smooth muscle because I knew as a student cyclic AMP would cause relaxation, and I suspected they were going to antagonize each other. That was my hypothesis at the time. But when we put azide hydroxylamine sodium nitrite on smooth muscle, airway smooth muscle, GI smooth muscle, vascular smooth muscle, cyclic GMP levels went up, but the tissues didn't contract. They relaxed. This was an interesting finding. There are always surprises in science. So I said, let's look at other smooth muscle relaxants and see what they do. So we then studied nitroglycerin, nitroprusside, and found that while they relaxed smooth muscle, and these are very old drugs, nitroglycerin was first discovered in the 1840s by Italian chemists. When chemists make compounds, they often lick their finger and taste the powder, and they would get headaches. So the physicians realized that this might be a vasodilator and started using it for angina, for heart attacks in the 1870s and 80s. And for 100 years it was used for angina. And we came along in the 1970s and figured out how it worked. And of course the Nobel Committee got excited because this was the history of the Nobel Prize. Alfred Nobel made all of his fortune from nitroglycerin, and now we figured out how it worked. So that got them interested. We came up then with a number of compounds that would increase cyclic GMP accumulation in tissues. We called these substances nitrovasodilators. A long list of substances, this is only a partial list. But we were able to determine that all of these substances were prodrugs or precursors to form nitric oxide in the tissue. And it was the nitric oxide that was doing all of the business, the biochemistry. And that's what was activating guanylyl cyclase to have cyclic GMP. Now this was heresy in the biochemistry field because nitric oxide is a pollutant, it's a poison, it's toxic. How in the world could it activate an enzyme? And a free radical, how could it activate an enzyme? It had never been shown before. Well, we proved that it did.